Okay, we're 1 minute past the hour, depending on where you are, the half hour. And can everyone hear me? Yeah, good. All right. I think we'll start. We'll make a start. So good morning from the Pacific region. And thank you for joining the 6th webinar for the USVs for GOOS community of practice discussions. This webinar series is very much about opening a dialogue between scientists who are using uncrewed surface vehicles to do ocean observing, and also with the private sector, so organizations who develop USVs. And so together, these two groups are really inherent in the success of the global uptake of USVs, and in particular, the USVs for GOOS global emerging global network. So a bit of background about Ocius. Ocius is the Observing Air-Sea Interaction Strategy, and we're a global group dedicated to increasing global observations of the air and sea interface. And we're developing an emerging global network of uncrewed surface vehicles that will sit in the future with the Global Ocean Observing System. And so Ocius is a SCORE working group led by Megan Cronin, Sebastian Swart, and Krista Marandino. And the USVs for GOOS is an endorsed UN Ocean Decade program. And if you'd like to learn more about Ocius, I encourage you to look at the website, which is here in yellow on the front slide. And of course, if you're interested in presenting or getting involved, please reach out on the website via the yellow link to the Get Involved page. And if you don't know a lot about Ocius and would like to know more, please have a look at the website. There are some previous webinars and it's a great place to find out more about the program and what we do. So could we have the next slide, please, Cassie? Yeah, so today we have a Pacific focus and we have two presentations. The first one is from Nick Rozenhauer. Nick is the Ocius Oceans Manager with Ocius, which is a company out of Australia that develops the Blue Bottle USVs. And we're also privileged to have Makio Honda, who is a biogeochemistry expert from JAMSTEC, and he'll be speaking today about the potential use of USVs in biogeochemistry. And Makio has extensive experience in open ocean biogeochemical observing, which to me, as a physical oceanographer, is quite always a bit of a mystery. So I'm very excited about hearing more about that. So without further ado, we will start with Nick. If Nick could you please share your screen and turn your mic on?
No worries. Can you guys see that? Hear me?
Yeah.
No worries.
Yeah.
Thank you, Ruth, and Megan, and also to Honda Sensei. A little bit of background about me. I work for Ocius. We're an Australian company. We build the Blue Bottle USV platform. And I guess the reason and the impetus for this presentation is that earlier this year, we worked with JAMSTEC, who Honda Sensei, and worked very closely with him to perform a sort of an oceanographic and bathymetry mission of two subsea volcanoes in the Pacific, about 1,000 kilometers south of Tokyo. And I guess the topic of the presentation is to kind of give you guys a bit of a recap, introduce you to the platform itself, but also to kind of, I guess, share the lessons learned that we learned from this mission, and sort of how we would approach it next time. So just quickly, before I start, I'll just for everyone's sake, kind of give you a bit of a background about who we are as a company and about our platform and dive in from there. So we've been focusing on USV development since 2015. The product itself was born out of an Australian Defence Innovation Grant for surveillance. So Australia has 8 million square kilometres of sovereign water, and we have 23 border security vessels to patrol it. So there's a bit of a mismatch here locally between resourcing and actually providing a coherent and coverage of our borders. And so the government essentially gave Ocius a grant to develop a vessel that would stay at sea indefinitely and be able to host a large payload. And the boat and a lot of the characteristics of the boat have been designed around that feature. We recently sold and built 5 to the Royal Australian Navy. But we do have, it is just a robot boat at the end of the day. So we are focusing on non-defense applications, particularly in the science and marine mammal observation and bathymetry space. And between Sydney, we build all the boats here in Sydney, but between Sydney and Perth, we have now 40 people working for us. So just quickly here, a bit of background. You can see the Blue Bottle, our flagship product here on the screen. So it's a renewable powered boat. It's powered by the wind. So it has a solar sail that articulates and provides propulsion. It's powered by solar power. So it has a 3 kilowatt electric motor that turns solar energy into propulsion. And then uniquely, it has the rudder at the front of the boat. And as all mariners, we know that's a bit odd, but on the rudder, it has a large appendage, which using the pitching of the vessel, it uses it to propel it forward. And the significance of that is that it can loiter or stay on station using minimal or no electrical load, which is significant in surveillance or different kind of applications. We've been approved to operate in Australia and Japan, and we've had 0 on-water incidences. And then I guess the impetus, or just rather, but out of necessity, the boat's been designed to be low logistics. So it can fit in a 40-foot shipping container. We can launch it from a boat ramp. We can launch it for a crane. We drive it around just using a normal SUV. So really low logistic. And I guess a significant advantage over, I'm sure everyone here is aware of sail drone. Well, we're kind of there's only a few players in this renewable energy sailing boat space. I guess one of the only big significant differentiators for us is that we can lower our storm. And so lower our sail rather. We can, and the significance of that is that from a surveillance point of view, you have tactical range advantage, but from a sort of a survivability, we can lower the sail in adverse conditions and survive them and stay on station. I guess the last point to mention is that the boat is designed to host 150 to 100 watts of payload power in normal sunlight conditions. I've just shared a really quick video just so everyone. So this is the wind power. This is one of our boats off Sydney here. And then wave power, so you can see the fiberglass appendage as it flexes, it provides propulsion. And then the boat is able to put its sail down and use the solar energy to propel it. I guess as a company, we've slowly but surely trying to ramp up and starting to operate the boats significantly. We've got over 900 days now at sea, and we've operated extensively out of the north coast, northwest shelf of Australia here. So we've done over 30,000 nautical miles, which is a bit over the lap of the earth. And the longest time we've had a boat at sea is 54 days. Which is more of a function of the customer requirement rather than the capability of the boat, because we are still a small company and boats at sea cost money, but we're actively trying to put a boat out there for 100 days just to show that we've done it. But the platform itself has slowly developed, and to a point where we are looking to other avenues, as I mentioned before, other industry verticals to apply the technology to. I guess that's sort of that's kind of the recap about us and the necessary salesy thing. But the topic and the reason I'm here to talk about today is the mission that we did with JAMSTEC in Japan. So the photo you can see here is of Nishinoshima, which is a subsea volcano that's come up, and it's just about 1,000 kilometers south of Tokyo. And this photo was taken from the blue bottle, so you can see pretty close. You can see the sort of water here and the steam and ash coming off the vessel here. I'll just play a little video while I talk to it, but this is essentially a recap of the mission. Why did JAMSTEC approach us? Is because it's too dangerous for crude ships to go next to these volcanoes. They're as they develop and as recently as 2021, they've had explosion events. Is that the topography is unknown, and so it's too dangerous to put cruise ships next to them, considering that they are still live. And so that's why really the boat was they approached us as a means to collect data. Wasn't just so the payload that we developed was it was a single beam echo sounder, sub bottom profiler, and side scan sonar that we've sort of refined and tuned in Australia before we went, as well as other oceanographics. So we had an Aquatrol 600, which had your dissolved oxygen, your pH. We also had water skin temperature, which was a Heatronics, and then your standard CTD, and then also wind speed, wind direction, and the like. And the idea was originally to do 2 missions, one to Nishinoshima, which is this closer volcano here that you just watched, and one to the southern volcano. How we structured the mission, I guess, was that we with JAMSTEC is that we said that for each day that they sort of paid for 60 days of data collection, sort of acknowledging the risks of with this sort of mission. It's super remote. It is quite challenging, and we would then be paid for each day of data that we collected, including a report at the end. Because we were operating in Japan, JAMSTEC did sort of the responsibility for getting regulatory approvals was on them, and we left that to them as part of the contract. I'll just go to the next one. So you can see here the appendage. So we were using our renewable powered version, a renewable powered blue bottle, and while it wasn't designed necessarily to host these brackets, to host these sensors, we constructed a bracket noting that the time frame that we wanted to do it in. As part of our sort of quality assurance test, we did go overseas. We did go to Perth, which is kind of quite a difficult. It has the similar topography as these subsea volcanoes, and quite a challenging destination that we thought would mimic Japan. And we did trial these sensors and test the quality of the data to ensure before we went that everything was working. And we partnered with a local company here, Guardian Geomatics, because as a company, we're kind of more interested in owning and operating the vessels and less about the bathymetry, I guess, and having that capability in-house. So to recap, I guess the mission itself is that when we did get there, so as part of our due diligence, I might actually just go back and forth to this slide here. As part of our due diligence, we got professional meteorological modeling, and we did all our calculations and everything. And the thing that we didn't account for and the models didn't reflect was the subsea currents. And so because it's a renewable powered boat, essentially when I say operate sustainably, what I mean is that we designed the payload and everything to operate such that the weather conditions from the irradiance from the sun would charge the batteries enough such that the boat could operate and host the payload, and it would able to, charge up more than it expelled. When we got to the on station, the undersea currents were significantly stronger than we had anticipated. So, and essentially what that meant though was that although the boat could run the lines and do it, it was expending too much power for us to actually complete the mission. And so what that ended up meaning is that we had to sort of do this Roomba kind of, this data collection style to mitigate these things, coupled with the fact that we saw two typhoons in the sort of the space of where we operated. The decision between the two parties was that we would postpone and then subsequently cancel the contract because we couldn't collect the level of data with the renewable powered vessel that we originally anticipated. I'm going to come back and talk to these. Something that we did offer, and as a company we internalized it, is that to run these significant payloads, and when I say significant, I'm sort of in the 100 and over 150 watts, and run these mission lines where you have to have quite specific line spacing, especially with a single beam echo sounder. We internalized that and have created this hybrid electric version. Now the boat here is in Australia. We have something called NOPSEMA, which is essentially our environmental offshore environmental regulator, and we've designed the boat such that it has the diesel allows it to, just the way that the technology and physics works is that it has such a high capacity to store energy rather than batteries, and so we've designed it to hold enough diesel that it still comes under the threshold where you have to report or you have to account for it in your environmental planning. So this boat has been developed. It's currently being sea trialed, and we did offer it to JAMSTEC. We understand that sort of the appetite to go back, it was extremely challenging. So, but our intention is to use this vessel for really bathymetry loads. And we would probably say, for the different customers, depending on what kind of mission we want. The challenges from that we faced as a company in operating this far, and I think because we are a small company, and this is really the first overseas and remote mission that we ran, was really the remoteness. I think it was something that we didn't account for. Chichijima is 24-hour, or pretty much a day's ferry ride south of Tokyo. It's also the ferry comes roughly about once every 4 or 5 days and a week. And while we did bring, these are so everyone can appreciate. While you can bring all your different spares and you can bring all your stuff, just the little stuff that you might not consider, it's just a week away. And so what we saw, even though the kind of things that are broken, it's sort of nominal in any sort of, even in Australia, in any of the locations that we've kind of gone to, there were only 1,500 people. There's not much infrastructure to do any repairs, and so the delay of having a week and then another week was something that saw our timeline sort of blow up. And so I guess for us, operating in these really remote regions just required a bit of a different thinking, and something that we've taken on board in how both we price our sort of missions, but also how we would design them differently such that we can support them better. The something we learned was that the payload redundancy, because we did have a third party come and do the bathymetry, and while they have used extensively USVs before, due to the remoteness and the like, having multiple forms of redundancy for your primary payload is something that we've taken on board, and that includes hard drives, computers, ways to access, and even redundant sensors to be installed on the boat, just so that the remoteness doesn't kill you. If you're missing a humidity sensor or something, you're not waiting a week before you can go out to have multiple forms on board. I guess something culturally that we also sort of and came across is that it was a different operating environment and one that we weren't used to. And so I guess for us, engaging with local partners to really fully understand the appetite of the local stakeholders to support these kind of missions is something that's super critical. And I think as we progress and do more missions, especially in the Pacific and around the world, it's having that local partnership to make sure that we're across all the different scenarios that can happen before we proceed, and just so that everyone's on the same page regarding the local appetite to support these missions and what we might need or what might happen, just so there are no surprises and we're not going there and saying, oh, well, can we do this? And they say, oh, well, we never expected you to ask this. Whereas, yeah, I guess, yeah, I think that was kind of the lessons that we learned in the recap. I'm just conscious of the time there. But we also enjoyed thoroughly working with Honda Sensei. He's an amazing man, and we had it was a great experience. And as a company, we're super appreciative of the opportunity and looking to work more in this space and help the Pacific and all the rest as much as we can. So thank you. Thanks for everyone's time.
Thank you. Thanks, Nick. That was a great presentation. It's really interesting to see and hear about the challenges, which, I understand you're a commercial company, and it was really, really good to hear the honest sort of challenges that you encountered. We do have a question online. I'll just go through a couple. Michael Jones from Subsea Sail. How big is the vessel and what does it weigh?
The boat is 7 meters and it weighs approximately a ton, depending. Okay. Yeah, pretty much.
Awesome. And next one is, can you give an approximate cost of data per day, basis and number of parameters? That might be a bigger question, but Nick, are you able to have a go at that, knowing that there's probably some, Yeah. Tell us about the sensitivities of that question as well, because that's always a question and it's never really answered.
Absolutely. And I mean, I have to give you the pub number, as my boss likes to say. It's the pub number but we kind of, including mobilization and demobilization costs, you're looking at 3,000 to 5,000 Aussie a day. Now that's for one boat, and as you scale up, the costs come down. But that's roughly what we've come sort of, that's roughly. And so I guess the sensitivities with that is we're interested in, as a company, owning and operating the boats, and we're payload agnostic. If you want us to find we have the capabilities now in-house to, if you are unsure about, you say, I want to measure X variable and I'm not sure, we can go and provide you a whole range of different options. Or you can provide your own equipment and we will happily install it and work with you to store and transmit the data as necessary.
Okay, great, thank you. That was quite a straightforward answer. Well done. We'll have time for a conversation after Makio's presentation. So if you have any further questions for Nick, there'll be time. I also realized I forgot to introduce myself. I'm Ruth Patterson. I work for Elysium EPL and I'm based in Darwin in Northern Australia. So let's move to Makio's presentation. Makio, would you mind please sharing your screen?
Okay, so I'll try like this. Does it work?
Yes, we can see that.
Yeah.
Okay. Okay,
Yep,
so
go ahead.
thank you. Okay, thank you, Nick. So good talk. Okay, so hello everyone, and thank you very much for joining. And Meghan and Kombina, thank you very much for inviting me to this webinar. So today I would like to talk entitled this potential contribution of USB to my biogeochemical study. Or just a second, pointer. Yes. Okay, so I am a chemical oceanographer. My main scientific target is to verify the ocean's role in controlling the atmospheric CO2 quantitatively. So, as you know, ocean plays a crucial role in global carbon cycle because ocean absorbed about 1/3 of annually emitted anthropogenic CO2, and ocean have stored about 60 times of atmospheric CO2. During the last 3 decades, I have been focusing on the mechanism called the biological carbon pump. The biological carbon pump is a mechanism that photosynthetically fixed CO2 is transported to the ocean interior by mainly settling particles called marine snow. In order to study the biological carbon pump, time series sediment trap observations have been conducted all over the world ocean. By deploying time series sediment trap at various areas and various depths, spatio-temporally variable marine snow can be collected, and after recovery the sediment marine system and samples, by analyzing collected marine snow chemically, biologically, and geologically, it can be verified when, where, how, and how much CO2 is transported to the ocean interior. Since 2014, I have been conducting sediment trap observation at NOAA P-MEL time series station Kio, because I would like to verify the reason why primary productivity in the subtropical oligotrophic poor nutrient area is comparable to or slightly higher than that in subarctic eutrophic area. So thanks to physical oceanographic data obtained by Kio buoy, it can be revealed that upwelling of nutrient-rich water by mesoscale cyclonic eddy paths result in increasing of subsurface primary productivity and marine snow observed by our sediment trap like this. On the other hand, it has been pointed out that transported carbon estimated by sediment trap cannot fill up carbon demand of creatures dwelling in the mesopelagic and basipelagic layers. Thus, the quantitative observation of CO2 transportation by small suspended or small slow sinking particles, which cannot be collected by traditional sediment trap, has been strongly requested nowadays. So the biological pump by small particles is called physically particulate injection pump, PIPs. It is expected that the PIPs might contribute to about 40% of total biological carbon pump. For this observation, new technologies such as the BGC Argo and Glider have been expected and used recently. So by this platform, optical observation of small particles has revealed that these particles are transported to the ocean interior by the mixed layer deepening and by downwelling caused by mesoscale eddy. So I would like to let USV observe these phenomena. Thus, as a carbon chemist, I am interested in the upper ocean interior rather than the sea surface. So if the USB is equipped with a profiler or winch system and CTD optical sensors such as a backscatter meter and other biogeochemical sensors. Spatial temporal variability of small particles in the upper ocean can be observed. I would like to deploy the USB with the profiler and conducted these observations around Station Kyo, located in the Western Pacific subtropical area, because this area is a strong sink of atmospheric CO2, as you can see, like this. In addition, this area is appropriate areas because lots of mesoscale eddy and typhoon pass through. As I mentioned, these events affect biogeochemistry. However, as you know, its observation is not so easy by ordinary research vessels and a fixed buoy or mooring system. The USB must enable us to study the impact of these events on the biogeochemistry. So finally, I have limited experience to use the USB. The first trial was American USB sail drone observation. In winter 2018, in order to verify its navigation ability and compare its data with Kyo surface buoy data, sail drone was deployed at Guam. So as you can see, sail drone successfully completed her round trip from Guam to Kyo. And sail drone successfully conducted the line transect observation around Kyo. And its data were generally comparable to Kyo buoy data. However, because of low power and damage by the vandalism, this observation cannot but be suspended after about a week observation. So this year, as Nick introduced already, we ordered Australian company Ocius to conduct their USB blue bottle observation of mainly bathymetry of the investigation around the Nishinoshima, which is a volcanically active and research vessels cannot approach. Blue bottle was deployed at Chichijima in May. So blue bottle bravely approached the Nishinoshima. So thanks to their activity, her activities of photographs like this and backscatter data obtained by blue bottles revealed that there was a change color area east side of Nishinoshima. However, this observation was also canceled after 5 days observation because of low power and strong current and frequent typhoon attacks. So as a summary, so I just proposed some study by using a USB. But if USB observation is conducted for this purpose, these issues should be overcome. So at least I need the profiler and the power and durability, avoidance of collision, and there is a strictly very, very serious Japanese regulation and cost some guy touch up on before. So that's all. Thank you.
Thank you, Makio. That was a really good presentation, really interesting presentation about biogeochemistry and the potential for USVs. It's great that you've had a go. Did you have your, I'm assuming that you haven't been able to put your sediment traps or the primary productivity traps on a USV yet, is that correct?
Not separately. My sediment trap is deployed separately. from USB. So just next to the NOAA KOV. So I utilize the KOV physical oceanographic and meteorological data. So I interpreted why the sinking particle increased. So according to some analysis, so upwelling caused by the mesoscale eddy path supplies the nutrient to upper layer, resulting in the increase of primary productivity and sinking particle like this. So it is very difficult to use a USB for the bathymetry phenomena, but and also, some consigned sediment trap collected the sinking particle in deep sea, but many people would like to know what is going on in the upper ocean. So in order to observe the biogeochemistry in upper ocean, USB might be helpful and useful. So this is a point I would like to say, yes.
Thank you. Okay, so that concludes the presentations for today. And now we have some time for open discussion amongst the panelists and the audience. So does anybody have a question? Please raise your hand and Cassie will alert me. We have a question here in the chat from Megan. Can anyone talk about the potential for other sensor suites? So I guess Nick or Makio, do either of you have experience in the other types of sensor suites as they would be, you know, put on a USV and utilized?
Yeah, and maybe could, I don't know if one of you has the diagram that has sensors on it and where it was located. I know I saw the wind sensor was behind the wing, and I'm wondering, you know, with the wind sensor behind the wing, does that cause, you know, aerodynamic changes to the measurement of the wind? And but you know, where could you put other sensors? And I guess also, you know, can you remind me again what the full sensor suite was that you were using, Makio?
So at this moment, I just conducted a test trial and just verify the ability of the USB. So I've never conducted my own science with using a USB, but in near future, and also as I emphasize, as for my science, the profiler is strongly requested. So I sometimes request a Celdron company when the wind system is available. So if the wind system is available nowadays, the very small sensor has been developed, and many biogeochemical sensor is already equipped on the BGC Argo float. So at least nutrient sensor and dissolved oxygen sensor and optical sensor, yes. So
you would,
yes.
you, sorry, you would be using the USV like a mobile BGC and not necessarily for the surface components that would be mounted on the keel or right. But it is a interesting. I'm wondering what meteorological sensors could be put on this platform, and maybe this is a question for Nick then. You know, where do you have the winds and air temperature and other measurements?
I'll just cover off. I think you asked for a few different things there, Megan. So maybe I'll just cover off in
Okay.
terms of go through the list. But in terms of talking about where you can put sensors on the boat, so we work with our customers and are currently working with customers to develop missions. And right now, all the wind gear is back here. When we do go sailing, we don't find that there is any there is any attenuation, but I know for a current customer who we're working to put a mission together here in Australia with, they've requested that we put a significantly taller mast on. So this one is about 1.5 meters, and we're going to put a 2.5 to 3 meter mast on, so we can get that air weather station unit above the reach of the sail, because they feel more comfortable with that. Now it comes with additional, we work together to essentially strap sensors as best we can. There's always going to be, just like anything, there's going to be pros and cons to the different setups. In terms of where on the boat, it is a vessel. We have hull mounted things before. I'll pull up this slide here. So for us, you can for the Japanese job, we hull mounted this bracket here because it was the sort of the best way that we could attach this payload that was quite extensive bathymetry payload to this boat. Sort of retrofitting it. We attached on this arm, we had the aquatrol, we had a backscatter, we had a little CTD profiler, the side scans and all of that. And so I guess really your imagination is the limit of where you want to mount a sensor. We are working to develop eDNA technology into the boat, and we've got funnels coming through the front of the keel, on the side of the keel, and we're working to optimize that. But really, we're led by the scientists. So that if you want a sensor, and we either bring that expertise in, if the scientists don't have it themselves, or we lean on to you as to where the best position for the boat.
So with the wind sensor, why don't you have it in the front? You have the wind sensor in the back. I mean, could you put it in the front?
We could definitely put it in the front. The only issue being then when you go downwind, you're going to have the same issue.
No.
As
then you're seeing fresh. Then I mean,
so
right now your wind
vessel,
sensor, your wind you're in the wake of the sail there. So you're not seeing the ambient winds.
So we actually do find that we're not attenuated, and we've compared it against a fixed station as to different sailing conditions, and we can provide people that data. But we found it depends which direction the wind and which way the boat is sailing. So if the boat is sailing downwind, then the wind will be behind and you'll be getting that fresh air. Alternatively, if you're going upwind, you might have, the spin, essentially the wash off the sail is going to be in that position. But because the boat sails at 50 degrees to because it's a sailing boat, it never goes into the wind with the sail up unless it's during attack. So we essentially, because it's always at 50 degrees, it is actually getting that fresh air, and the apparent breeze. Sorry, this is going into too much detail. The apparent breeze is never back enough because we never go fast enough to actually create any apparent, and so the wind is fresh. The only time we do get disturbed wind is through attack, and that's just something that we've marked in the data. So we just have, in the way that we report it over a Mavlink message, it just says tacking. And so if we're recording at a hertz and a tack takes 3 seconds or whatever, whatever fresh rate, it just has a flag next to it, so that if someone did want to emit any data where we believe that it was going to be affected, it would. In terms of then the considerations here, in terms of the payload, I saw a question on the chat of the weight. We can hold up to 300 kilos. Essentially, I should really get an image of the renewable powered boat, but this sensor here, this whole payload here, when it's not full of this engine room, is actually all for the customer. So we have one box in there. And so that whole payload bay is for whatever you want to put into it. We can hold up to 300 kilos, and it's a massive area. As someone who's built the boat, you routinely have lie down in that area. And I'm not that big, but I'm not that small, so it's quite a large area. And then I guess on the things that you consider, the other kind of sensors for everyone's thing. So we are towed arrays is probably a large thing. So we do have the ability to retract an array into the keel on the renewable powered boat. That's been kind of the focus of the company from a defense application. So we've worked considerably with that to get a profiling array as well as an acoustic hydrophone array. And we just recently ran a trial with JASCO Applied Sciences to do passive acoustic monitoring for marine mammals. And as well as eDNA that I touched on before. I guess they're the kind of sensor suites that we have investigated with, but really it's limited to the imagination. And then to round out the last bit for the sensors for all USV, for anyone who's thinking about using a USV, I think it's the thing that is really challenging is this power, especially with the renewable power boats, is this power versus data bandwidth versus less so the size. And so I think it's really a matter of a power draw thing because they are renewable. And when you're out at sea, hundreds of miles from shore, you don't really have a choice. Yeah, if the conditions are adverse for long periods of time, if conditions are adverse for long periods of time, you run the risk of having to abandon the mission to go and charge the boat or really. So something that we, I guess, consider now really carefully is working to make sure that there's primary sensors that are, of the utmost importance that will always be switched on, and then developing a payload package to support, and where possible using like sensors that have their own power supply to so that we can support the sensor suites that people desire.
Are there other people? I don't want to be kind of taking more than my turn here with questions, but I do have more questions.
There's one question on the chat, but go for it, Megan. We'll leave some time at the end.
Do you have IMUs so that you're able to transform your wind measurements from the platform coordinate system into Earth coordinate systems at 10 hertz, 20 hertz timescales?
Yeah, we have I think we have 6 IMUs on board and using a mesh. We do that.
Okay, so the chat question is, Nick, is the hybrid boat an actual product or just a concept right now?
It is an actual product. It is actually sea trialing with some Norbert multi-beam echo sounding equipment as we speak. It is going to be Kongsberg's multi-beam 2040p is going on in the new year. And we are, in Australia, there is a fair significant bit of interest to support the renewable energy sort of developments, a lot of offshore wind. And there is a new mandate from a lot of these companies to do it as ecologically minimal as possible. And so I think it's still a prototype, we're still building it, we're learning a lot, but it's an actual thing.
Thank you, Nick. I have a question for Makio. I'm wondering, what do you need to see as evidence from lots of the USV companies to show that that you can sort of trust the capability? Do you need to see academic papers? Do you need to see scientific articles about how the USV performs? Like what is it that you need to see to be confident that you're engaging the appropriate USV company and USV technology?
At this moment, I cannot find which USV is most strong candidate. But already, for example, yeah, previous webinar, Ocean Aero company was introduced their own USB. Their good point is they USB can dive. Not only, I think, yeah, that is the main purpose is to escape from the hurricane or rough sea. But if the USB can dive, maybe some data under the water, I mean the data in the upper ocean interior can be obtained. So there is a much possibility, but at this moment, it is very difficult to judge which USB is strongest candidate. And also, yeah, at this moment, about the biogeochemistry, I read only the paper about the, the Adrian Sutton, ASB CO2. Yeah. So expect this paper I've never seen some biogeochemical study by using a USB, but in near future, I hope if USB is deployed as a mesoscale ready place, and if successfully USB can obtain some vertical profile of optical data or some change in the mixed layer depth or something. So maybe it becomes a good paper, I think, yeah. But at this moment, only the ASV CO2 developed by Adrian Santo is only one for my field. Yeah, I can say so, yes.
Do you think the USV developers should be involved in the academic or scientific papers so that they can understand what the intricacies of the data that you, and the information that you're collecting and have to show?
Just a second. Web grade.
Ruth, can I say yes to that, with especially with the intercomparisons, interoperability. I think it does it is nice to work with the the USV developers and have them be part of the testing. But yeah, you have a question in the chat there.
Yeah, so maybe, yeah, web glider is also useful as long as, yeah, web glider has a 150-meter winch. Yes, it works. But maybe to compare with the web glider, USB can sail more faster. So this is a benefit to use USB. So maybe web glider also can be used for my science, but I hope, yeah, in the future, USB with winch can be available for biogeochemist.
There's also a comment here from Michael B. Jones. Subsea Sail has a vehicle. The subsea sail vehicle was explored in a previous webinar, and the whole thing submerges, and the sail sort of acts like a drogue, so they can submerge to 100 meters. What's your limit? What's your? I noticed that you mentioned both the What's your depth limit or maximum?
So
Makio,
according to the sail drone brochures, two types. One is a 200-meter and another one is a 500-meter. But 500-meter winch is equipped on the big size sail drone, whale size giant sail drones. And also, yeah, Nick, so Ocius winch have a 200-meter wire length. So if in your future, such kind of a sensor is installed at the top of the winch, maybe 200-meter observation is possible. I hope so.
Great,
Yeah,
thank
just
you.
one-
And
Oh, Ruth,
Sorry,
just to jump in, but just as like from the USV manufacturers, and I know some Michael here and stuff. What's it called? How am I sharing my Explorer? There you go. Looking up the subsea. The working with scientists, so having that dialogue even before, even if you're just thinking about, oh well, maybe this USV technology could be useful, for us to understand and have that time before the mission to actually maybe that's part of that dialogue that I know we've internally taken in these science missions to say, what's the actual deliverable at the end? What paper are you hoping to write? Because because I guess it helps us create a better product and helps us empathize with, okay, well then this is really what you're trying to create. This is X, Y, and Z. And yeah, I think maybe that's a lesson for all USB manufacturers or potential scientists entering the field. Sorry.
Yeah, the comment
Okay,
in the chat. Yeah. I watched the subsea sail on the YouTube previous webinar. So maybe, I'm very interested in that. But it depends on the area and the season, which depth is enough for my science. So in summer seasons, mixed layer depth is very, very shallow. On the other hand, in winter season, especially in the subtropical area, mixed layer depth becomes 300 meter, 400 meter. So if I would like to know what is going on below the surface mixed layer, so 100 meter is not enough sometimes. So it depends on the area and the season.
I think if you want to do, hundreds of meters, you're probably talking about an unmanned underwater vehicle. We're really focused on the air-water interface, and then we're able to drift, go underwater. So we're very ultra quiet, and we can go to any depth down to 100 meters. Later, we just haven't had people ask go down deeper. The pressure at 100 meters is 150 psi, and so it just requires some strengthening. But the ability to go down, and our vehicle is only 23 kilos, so we're very easy to put in the water, get out of the water, and it's usually at a price point that people can put multiples of vehicles out. Anyway, happy to talk to you offline.
Okay, thank you. Good to know. Thank you very much for good information.
Could I ask a question,
right.
Michael?
Oh yeah, last one. But for those who need to leave, we are on the hour, and thank you for attending. But I'm happy to keep this open for another 5 or 10 minutes, if that's okay with you, Cassie.
Well, we can take the conversation offline. All right, we'll go past it.
It's the end of the day where Cassie is now, so she probably wants to get home. So let's leave it there, and please continue to be involved, everyone, and reach out. All of these conversations are extremely important to the community and the network. And if anyone's interested in or attending the Ocean Sciences meeting in New Orleans in February, we are having a workshop for Oasis and the USVs for GOOS, where we intend to put a lot of this type of information into an academic paper to pull out best practices as kind of like a guide that both USV developers and scientists can use to forge the future using USVs across the globe. So we hope to see you there, and if not, we'll see you in the next webinar. Please reach out if you would like us to focus on a topic, or if you'd like to volunteer to speak. We're always looking for speakers. So thanks everyone, and we'll see you later.
Thank you.